So today we are going to discuss dimensional analysis, and dimensional analysis is very interesting technique for whenever we conduct experiments. And what it does, it helps us in reducing the number of experiments and combining different variables into dimensionless terms. So what does that mean? We will come to that in a little bit. What we have done so far is the control volume analysis. We have done the control volume analysis in which we took a finite control volume and we wrote a Reynolds transport theorem for that finite control volume, and then we derived different type of Reynolds transport theorem for mass conservation, energy conservation, and momentum conservation, and then we applied that accordingly to different situation of in our fluid kinematics. Then we dived a little bit deeper in detail and we derived differential equations for those mass conservation and momentum conservation principles, and how for a small infinitesimal particle or for a single fluid particle we also derived equation of motions. So these two techniques, the differential analysis and the control volume analysis, these are analytical techniques in which we use equations to solve a certain problems. But fluid mechanics does not rely on just these two techniques. In fluid mechanics or in any engineering problem, what we need to do, we need to conduct experiments to see the effects of certain variables on a certain other variable. So experimental analysis is key to any science, and to conduct experiments we need to conduct them in a very efficient manner, because experiment cost a lot of money and time. So experiments are very expensive, and we need an efficient way to conduct them. What does that mean? Let's see an example. Let's say we have a pipe, and this pipe is placed in your, let's say, in your fluid mechanics lab, and what we are interested in is the pressure drop in that pipe. So let's say we have section 1, section 2, and there is a fluid that is flowing in this pipe, and what I'm interested in is the pressure drop from section 1 to section 2. So what will this pressure drop depend on? What are the variables on which this pressure drop depends on? So let's say I say that this pressure drop, this pressure drop per unit length, that is delta P per unit length, depends on the diameter of the pipe, the density of the fluid, the viscosity of the fluid, and the velocity of the fluid. So here the pressure drop per unit length is dependent on 4 variables. So in total we have 5 variables. One is the pressure drop per unit length, the other is the diameter, the density, viscosity, and velocity. So in total we have 5 variables, and we want to see the effect of these 4 variables, that is the diameter, density, viscosity, velocity, on this one variable, that is the pressure drop per unit length. So this is the dependent variable. This is dependent on the diameter, viscosity, density, and velocity of the fluid, and these are the independent variables. These are the independent variables. So for a thorough experiments to see the effect of the diameter, the density, the viscosity, and the velocity on the pressure drop per unit length, what we need to do is to fix 3 variables. If we are talking about these independent variables, for any thorough experiment to see the effect of each of them on the pressure drop per unit length, what I will do is I will fix the diameter, I will fix the density, I will fix the viscosity, and then I will change the velocity. Let's say I change the velocity 10 times, 1, 2, 3, 4, and so on, 10 times. Then I will fix the velocity, the density, the diameter, and I will change the viscosity 10 times, and so on and so forth. For other variables, I will fix the diameter, the viscosity, and the velocity, and I will change the density of the fluid 10 times. Then I will fix the density, the viscosity, the velocity, and I will change the diameter of the pipe 10 times. So if I am changing each of these variables 10 times and fixing the other 3, I will end up with 10 to the power 4 experiments, and these are equal to 10,000 experiments. So if I start conducting 10,000 experiments, this will cost me a lot of time and money. So I need a smart way of doing this. I need a very smart way of doing this. I need to reduce my number of experiments, and by reducing my number of experiments, actually I will save a lot of time and a lot of money. So this is what dimensional analysis does. Dimensional analysis helps us do that, and it helps us reduce the number of experiments. So by dimensional analysis, what we are allowed to do, we can group these 5 variables, these pressure drop per unit length, the diameter, the density, the viscosity, the velocity, into dimensionless terms. So I can group these variables, the dependent and independent variable, into these 2 terms. One term right here and the other term right here. And if say I call this term pi 1 and I call this term pi 2. So now instead of 5 variables, I have 2 variables, that is pi 1 and pi 2, and this pi 1 is related to pi 2 by a certain constant. This is a constant. This right here is constant, as it is right here. So what I have done, I have took these 5 variables and I arranged them as such so that I can get just 2 variables, and I call these variables pi 1 and pi 2. So how will we do that? This is what dimensional analysis is all about, and what I have done, how will I arrange these terms? I will arrange these terms so these terms come out to be unitless. These terms right here, this term and this term, their units, all of these variables, the diameter variable, the pressure drop per unit variable, the density variable, the velocity variable, on the left hand side, if I write their units, they will come out to be unitless. These units will cancel out each other, and this term will be dimensionless. And this term will be dimensionless. And so also the term on the right hand side, it will also be dimensionless. If I write the units of density, the velocity, the diameter and the viscosity, these units will cancel out each other, and this term will also be dimensionless. How will they be dimensionless? We will see that in a little bit. So what I need to do in dimensional analysis, I need to first define my independent and dependent variable. Here I define my independent variables as my diameter of the pipe, the density of the pipe, the viscosity, the velocity of the fluid, and my dependent variable was the pressure drop per unit length. And I combined these 5 variables, 1, 2, 3, 4, 5 variables in such terms that these terms came out to be dimensionless, and then I equated them with the help of a constant. So this is what we will do in dimensional analysis, and we will use our basic equation of units, and this basic equation of units require us to remember that our basic dimensions, that any physical quantity can be represented in terms of its basic dimensions, and the basic dimensions were mass or force and length and time. So our basic dimensions can be mass, length, time, or force, length, time. We can either use mass as our basic dimension, but we can also use force as our basic dimension. Why? Because force is equal to Newton, and Newton is equal to kilogram meter per second square. So I can write this as ml t power to the minus 2. So this is what force represents. So I can also represent mass in terms of force, like m is equal to f L inverse and t to the power minus 2. So I can also represent mass as such. So I can use these 2 terms interchangeably, but I will use the other 2, that is the length and time, as such. So these are our basic units, the mass, length, time, or the force, length, time. With the help of these basic units, I will define my dimensionless terms, and these are the basic units that define any physical quantities. And any physical quantities, if you look at their units, they comprise of these 3 terms, that is the mass, length, time, or the force, length, time. So this is what I'm going to do. I'm going to use my knowledge of basic dimensions, and I'm going to write their dimensions and write them as such to convert the terms into dimensionless forms. But before that, I have to combine them into dimensionless manner. So how are these 2 terms dimensionless? Let's see that. For the term on the right hand side, the term on the right hand side is this one. this one right here. So the term on the right hand side, if I start writing the units of density, so density is mass per unit volume, and mass here is represented as force, as I told you. So force represented as mass can be F is equal to kilogram meter per second square, and mass will be equal to force, length, and T minus 2. So this is mass per unit volume, so it will become F L, and per unit volume will be per unit volume, this is the volume, so volume will be L cube. L cube will come up to the numerator, so it will be L minus 4. So the density will be in the form of these units as is represented right here. So this is what my density is, and then my velocity is meter per second. Velocity is meter per second, and meter per second can be represented as L T inverse, and the diameter is represented as length, and the viscosity, that is the dynamic viscosity, is represented as pressure Pascal into second, and Pascal, as you know, is force per unit area into second. This is the unit of viscosity, and force per unit area can be written as Fl minus 2, and second is T. So this is what is written here. I have made one mistake, and this is not minus 2, this is square. This right here is square when I write force in terms of right here. So this is how we write the units of these terms, and then if I start cancelling out these units, so it will come out to be dimensionless. These units will cancel out each other, and this term will be unitless. It does not will have any unit, and it will also be called dimensionless. So this is how this term on the right hand side of this equation is unitless. The force will cancel out with the force, L minus 2 will cancel out with this, it will combine with this L square, and the minus 2 will further be cancelled out. This T square will be remain to T, and T into T minus to the power 1 will cancel out. So we will be left with these terms. So this term represent that the combination of these variables is dimensionless. This is now dimensionless. So I have combined these variables as such, so they became dimensionless. Now let's see how the term on the left hand side of the equation that we wrote is dimensionless. If we take this term on the left hand side, and let's see how is that dimensionless. If we add the units of diameter, the pressure drop per unit length, and the density and the velocity, we will come up with this same result, and this is also dimensionless. Here you will be confused that the pressure drop per unit length is represented as such because pressure drop per unit length is represented like this. So pressure is force per unit area, so it is F over L square, and per unit length will become 1 over L, so F will give us F over L cube. So this is the pressure drop per unit length, this is the unit of diameter, this is the unit of density as we already discussed, and the unit of velocity. So if we cancel out these units, we will have a dimensionless term. So this is what we are going to do. We are going to define our key variables, our dependent and independent variables at start. If we, let's say we just repeat what we did, so that you might have a better understanding of what we are doing. For this example, we were talking about the pressure drop per unit length in this pipe. So the pressure drop per unit length was a dependent variable, and that dependent variable was dependent on the diameter of the pipe, the density of the fluid, the viscosity of the fluid, and the velocity of the fluid. And what we did, we combined these 5 variables into 2 terms, this term and this term right here, and these terms are dimensionless, as we can see from here that how are they dimensionless. So we combine our key variables into dimensionless terms and equate them with the help of a constant. So instead of having 5 variables, we have reduced our variables to 2 terms, that is pi 1 is equal to pi 2. So now we have 2 variables and we can work with 2 variables. So we have reduced our number of experiments, and we will do that by using the basic knowledge of our basic dimensions, and our basic dimensions can be mass, length, time, and if we can represent force and mass in terms of force, our basic dimensions can be force, length and time. So by using our knowledge of our basic dimensions, we will combine these dependent and independent variables and will convert them into dimensionless terms, and by doing so we will be actually reducing our number of experiments, and by doing so we will be actually saving a lot of time and money, and this is what we are going to do in this lecture. And to do that we need to study the Buckingham Pi theorem. The Buckingham Pi theorem gives us the method so that we can combine terms like this into dimensionless form. So this is what Buckingham Pi theorem does. It gives us a method in which we combine our dependent and independent variable into dimensionless form and equate them in the form of a equation. So this is what we are going to study today, and just to give it a final touch, dimensionless products, as you can see, these are the dimensionless products, are important and useful in planning, execution and interpretation of experiments, because now you can see from here that we have reduced the 5 variables into combined them into 2 terms. So we have reduced them from 5 to 2 terms, and by reducing them from 5 to 2 terms we have reduced the amount of time needed to conduct the experiments and the expenses that were required to conduct these experiments. So this is what we are going to study, and we are going to study that how are we going to combine these variables in our dimensionless form and then relate them like this with the help of a Buckingham Pi theorem. So now let's move forward and see what the Buckingham Pi theorem is. So as we already discussed, our dimensional analysis is based on the Buckingham Pi theorem, and what the Buckingham Pi theorem does, it helps us to reduce the number of variables that are involved in an experiment. So let's read out this statement. If an equation involving k variables is dimensionally homogeneous, what does that mean? That let's say if this was our equation that we wrote for our pressure change per unit length in the pipe, and we saw that the pressure change per unit length or the pressure drop per unit length was the function of diameter of the pipe, density of the fluid, viscosity of the fluid and velocity of the fluid, then the k variables are these variables, these dependent and independent variables. So in this case you can say that k is equal to 5, that the total number of dependent and independent variables are 5. So if the equation is dimensionally homogeneous, it can be reduced to a relationship among k minus r independent dimensionless products. So it can be reduced if this equation is homogeneous, and these dimensionally homogeneous k variables can be reduced to k minus r dimensionless independent products, where r is the minimum number of reference dimensions required to describe the variable. So we need to define r to understand the statement. So r is the minimum number of reference dimensions required to describe the variable. So these variables, as you can see, is the pressure drop per unit length is defined by these reference dimensions, that is FL in this case, and the diameter is represented by length L, the density is represented by FLT, and the viscosity is represented by FLT, and the velocity is represented by L and T. So what we need is we need a minimum number of reference dimensions required to describe these variables, and the minimum number of reference dimensions we need can be seen from here, that we require a minimum number of 3 reference dimensions, that is F, L, T, to actually describe these 5 variables and write their dimensions. So these are the minimum number of reference dimensions that are required, and this is what r is. R is equal to these minimum number of reference dimension, and r, as you can see, is equal to 3 in this case. So what will be k minus r? K minus r will be equal to 2. So the Buckingham Pi theorem, as in this case, helped us to reduce our number of dependent and independent variables from 5 to 2. And as you can see, as we previously wrote this equation, these are those 2 terms. This term right here and this term right here. This term will be called pi 1 and this term will be called pi 2. That's why we call this Buckingham Pi theorem. And pi 1 will be equal to pi 2 by this relation. So again we have reduced our number of variables from 5 to 2. So by actually working with 5 variables, we are now actually working with 2 variables, and this is what the Buckingham Pi theorem does. It helps us define the minimum number of variables that we need to actually see the effect of their dependent and independent variables on each other. And this principle is based on dimensional homogeneity. Dimensional homogeneity is very basic, and we have studied this in the first chapter, if you recall, of fluid mechanics. And dimensional homogeneity states that for any equation, the left hand side of the equation must be equal to the right hand side of the equation. So this is what dimensional homogeneity states, and this is what this theorem is based on, that the left hand side of this equation must be equal to the right hand side of this equation. And as you know that the left hand side is dimensionless, so the right hand side must also be dimensionless. So the two pi terms that we need to actually combine these variables must be dimensionless. So what we need to do, we are now required to combine these terms in such a way so that they come out to be dimensionless. And now in the coming section we need to determine these pi terms, and we will now see that how are we actually combining these terms, these dependent and independent variable, into dimensionless form. So now let's move on and do that. So now let's go through the steps through which we will be able to find our pi terms, and we will continue with the same example in which we are going to see a pressure drop in a pipe, and the key variables, the independent variables, are the pipe diameter, the velocity of the fluid, the density, and the viscosity of the fluid, and the dependent variable is the pressure drop per unit length. So step 1 is to list all the variables that are involved in the problem, and as we already know that these are our variables. This is the pressure drop per unit length, the diameter of the pipe, density, viscosity, and the velocity. These are our variables that are involved in this problem. In the second step, we will express each variables in terms of its basic dimensions. So we know that our basic dimensions, as we saw, can be FLT, that is for force, length, time, or MLT. So we will represent these variables in terms of these basic dimensions, and let's do that. So this will be the basic dimensions of pressure per unit length. So this will be P over L. This is the diameter dimension, which is length. This is the dimension for density, for viscosity, and for velocity. So in the second step, we will express each of the variables in terms of its basic dimensions. In step 3, what we are going to do, we are going to determine the required number of pi terms, and that we are going to do by using the Buckingham Pi theorem, which is K minus R gives us the number of pi terms that are required, and as you know, K are the number of variables that are involved in this problem. The number of variables, and as you know, the number of variables are 5 in this problem, both including the dependent and the independent variable. This is the dependent variable, and these 4 are the independent variable. So K is equal to 5, and R is the minimum number of reference dimensions that are required to represent these variables. So the minimum number of reference dimensions, as you can see, are F, L, and T. You know that F, L, T are the minimum number of reference dimensions, as we already discussed in the previous slide, that are required to represent all these variables. So the number of reference dimensions are 3. So by using the Buckingham Pi theorem, that is K minus R, this will give us the number of our required terms. So we require 2 pi terms to combine these variables in dimensionless form and create 2 pi terms. So this was our step 3, in which we used the Buckingham Pi theorem to identify the required number of pi terms. So now move on to step 4. So let's move on to step 4. In step 4, what we are going to do, we are going to identify our repeating variables. So what is meant by repeating variables? As we saw in step 3, we have two pi terms. We will have two pi terms, pi 1 and pi 2. With the help of Buckingham Pi theorem, we identified that we will have two pi theorems by the formula k minus r, and repeating variables will be those variables that will appear in both of these pi terms. It will appear in pi 1 and it will also appear in pi 2. But what will be the number of these repeating variable? Their number will be equal to the number of reference dimension. And as you know, our reference dimension, the number of our reference dimension is 3. R is equal to 3, and these are our 3 reference dimension. So what we need to do, we will select 3 repeating variables from our 5 variables that we have, and these are our variables that we have. So what we cannot do, we cannot select this delta p here because it is a dependent variable, and this dependent variable will appear once either in pi 1 or in pi 2. So this is a non-repeating variable. We will select 3 repeating variables from this list of independent variables, and we will select those variables whose dimensions are relatively easy. For example, the dimensions of diameter is length, which is relatively simple. The dimensions of velocity are meter per second, which is relatively simple. The dimensions of density is mass per unit volume, which is relatively simple. So I will select my 3 repeating variables as the diameter, density and velocity. These will be my 3 repeating variables, and I will have then I will be left with 2 non-repeating variables. One will be the pressure drop per unit length and the other will be viscosity. So the pressure drop per unit length and the viscosity will be my non-repeating variables, and velocity, density and the diameter will be my repeating variables. So they will appear both in pi 1 and pi 2. The diameter, density and velocity will appear both in pi 1 and pi 2. So this was my step 4, in which I needed to identify the repeating variables. So let's move to step 5. In step 5, what we need to do, we will multiply these repeating variables with a non-repeating variables and also raise their power to a certain exponent and then equate them to a dimensionless entity. So what does that mean? Let's form our first pi term by multiplying our non-repeating variable, that was our pressure drop per unit length, with the repeating variables that we just selected in step 4, that is the diameter, velocity and density, and we will also raise the power of these repeating variables to certain alphabets, that is A, B, C. So as you noticed, we raised the power of our repeating variables to certain exponent, and now we'll equate this term. We will write this term in dimensions form, and then we will equate them to a dimensionless entity like this. This is what we did. We wrote the dimensions of each of these variables. This is the dimensions for pressure drop per unit length right here, then the dimensions of diameter, that is length, then the dimensions of velocity, then the dimensions of density, and equated them to a dimensionless entity. These are our reference dimensions, and each raised to the power of 0, which makes this term dimensionless. And this is what we are doing. We are forming a pi term that will be dimensionless, and by getting our values of A, B, C, we will actually be able to rearrange this pi term so it will become dimensionless. So how we are going to do that? We are going to find the values of A, B and C now. And how are we going to do that? We are going to take each reference dimensions and add their powers. So here in pressure drop per unit length, what is the power of 4 or the exponent of 4? It is of force is 1. Here the exponent of force is 1, and here the length dimension does not include any force. Similarly, the velocity dimensions does not include any force term, and here the density dimensions include the force term, and its power is equal to C. So 1 plus C will be equal to the power on the right hand side of the force, and that is 0. So this is how we are going to form equations for our ABC terms by taking our dimensions, our reference dimensions one by one. So this is for the fourth dimension. Then I will take the length. So here the power of length is -3. Here the power of length is a plus a. Here the power of length will be b due to this bracket, so it will be plus b. And here the power of length is -4 multiplied by c, so this is -4c, and here this will be equated to 0. So this is for length. Then I will write the same for time. I will do the same for time by taking their power, and here the time will be -b, and here as you can see it is 2c plus 2c is equal to 0. So with the help of these three equations, I will be able to find the values of a, b, c, and then I will put the values of a, b, c right here, and this will give me the correct order of this pi term, which will be actually a dimensionless entity. And let's do that. Let's find the values of a, b, c, and before doing that, let's mention these equations in a little bit clean manner so that you might understand. This is the equation for c by taking the power of the force terms. This is the equation by taking the power of L, that is the length, and this is the equation by taking the powers of time. So by solving these three equations simultaneously, we will get our values of a, b, and c. So a is equal to 1, b is equal to -2, and c is equal to -1. So now let's put these values right here. Let's put these values right here. So a is 1, so pi 1 will be equal to now the change in pressure per unit length. D have a power of 1 now, so it will remain in the numerator. The velocity will have a power that is -2, so it will drop to the numerator, and the density has a power of -1 now, so it will also drop to the numerator. So this is our first pi term, and this is a dimensionless entity now. So now you understand how we form our pi terms, and this is our first pi term. We also need to find another pi term, and we will repeat the same procedure for finding pi 2. We will take our next non-repeating variable, and the next non-repeating variable is our viscosity, and we will multiply it with our repeating variables, that is our diameter, density, and velocity. And then we will do the same procedure for that. We will write in dimensions form, and we will equate that to a non-dimensional entity, and then we will find our values for a, b, c, and also arrange pi 2 in a dimensionless form. So let's do that. This will be our pi 1. This is the correct arrangement of pi 1, and if you write the dimensions of each of these variables, you will actually get a dimensionless number. So now in step 6, let's repeat step 5 for the remaining non-repeating variable, and the remaining non-repeating variables was our viscosity. So we took viscosity and multiplied it with the repeating variable that were diameter, velocity, and density, and then doing the same procedure, writing them in the reference dimension forms, each of these terms, each of these variables, and equating them to a dimensionless entity, and then equating the values of a, b, c by actually adding the powers for each of these dimensions, the reference dimensions, and getting the values of a, b, c. We can now form our pi 2. So these are our next, this is our next pi term, our pi 2 term, and this is it. We got our 2 pi terms that we were actually looking to find. And in step 7, what we are going to do, we are going to check all the pi terms that we find. So we actually computed 2 pi terms, that is pi 1 and pi 2. So we will recheck. We will actually recheck that are they dimensionless and independent. So what we need to do, we will write them At this point, stop and check to make sure the pi terms are actually dimensionless. So this is our step 7. We will check using both our reference dimension, that will be in FLT form and MLT form, and thus we will write our pi 1 terms and we will actually see that is it dimensionless or not. So if we look for pi 1, so it actually comes out to be dimensionless, and similarly for pi 2 it will also come out to be dimensionless. And alternatively, and this is for FLT, and we will also see that for MLT. So for both of our basic dimensions, these pi 1 terms and pi 2 terms come out to be dimensionless. So this is what step 7 is also telling us to do. And in the last step, finally in step 8, we can express the result of the dimensional analysis as such. This is pi 1 is equal to pi 2. This is what we initially saw, and now we can actually relate to this equation and relate to these terms, that how we arrange these terms as such in a dimensionless form by following this 8-step procedure. So this is how we came up with this equation, that pi 1 is equal to sigma pi 2, and initially we had 5 variables and now we have only 2 variables. So this is what dimensional analysis was all about. We talked about the experimental analysis, that dimensional analysis helps us with the experiments by reducing our number of experiments. So this is how it helps us to reduce our number of experiments by reducing the number of variables from 5 to 2. And we can also write our pi 2 right here, as you can see that the pi 2 term right here, as you can see, the values in the denominator are switched to the numerator and the values of the numerator are switched to the denominator. You can also write pi 2 like this. It does not make any difference. The result will be same. The result will come out to be dimensionless. So this is just another way of representing things. It will still be dimensionless. So this is what our final result will be, and this is how we get our pi terms and then equate it in a form of equation, that is pi 1 is equal to pi 2. You will be wondering that what will be the value of this constant that we are getting in these equations, that what will be the value of this constant. So to get the values of this constant, what we are going to do, we are going to run some experiments. We will run some experiments, and from that experiments we will get our values of diameter, pressure drop per unit length, density, velocity, and viscosity. And if once we got the values of these terms, we can actually use the same equation and we can actually compute our constant. So to compute our constant, we will have to run our experiments 1, 2, or 3 times to see the what the actual value of this constant will be. Then we will fix this value of the constant, and then we will use this equation to see the combined effect of this diameter, density, viscosity, and velocity on the pressure drop per unit length. And this will make our analysis, our experimental analysis, much easier, because as we initially mentioned, from 10,000 experiments we are actually reduced to quite few numbers of experiments. So this is how we have done our dimensional analysis. Initially we identified our key variables, both our dependent and independent variables. Then we wrote them in our reference dimensions form, or in our basic dimensions form, that was our FLT. We wrote them in the dimensions form. Then we identified our pi terms by using the Buckingham Pi theorem. Then we identified our repeating variables. Then we multiplied the non-repeating variables by repeating variables and formed our pi 1. Then we repeated the same procedure for pi 2, and then at the end we just cross-checked that to see that actually our pi 1 and pi 2 terms are actually dimensionless, and then at the end we equated them like this. So this was our dimensional analysis, and hope you understand that. and in the next lecture we will do an actual example. So let's move on to that.